Have you ever looked up at the night sky and wondered what's going on up there? It's a big place. For thousands of years humans have gazed at the stars, humans have gazed at the wandering planets trying to make sense of their celestial dance. Did you know that Mercury, the planet closest to the sun, gets so hot on its sunny side it could melt lead, but on its dark side it's colder than a freezer? That's wild. This extreme behavior is a clue that space doesn't always work how we'd expect. For a very long time, the smartest people thought planets moved in perfect circles around us. It was a beautiful, simple idea. The only problem? It was wrong. That mistake held back our understanding for centuries. People built incredibly complex models with circles on top of other circles, epicycles, all to force observations to fit the perfect circle theory. It was like trying to fit a square peg into a round hole, except the peg was Mars, and the hole was our cosmic model. Then came Johannes Kepler in the early 1600s. He wasn't just a casual stargazer, he was a mathematical detective. He had a mountain of evidence from his mentor, Tycho Brahe. He crunched the numbers, he drew the diagrams, he tested theory after theory, determined to find the truth. He realized planets weren't moving in perfect circles. They move in ellipses that match the data and unlock the cosmos. So, let's dive. Kepler's first big idea, his first law of planetary motion. It's elegantly simple. Planets orbit the sun in ellipses, with the sun at one of the two foci. Now, what's a focus? Imagine a string. Imagine two thumbtacks. Stick the thumbtacks into cardboard, loop the string around them, draw with a pencil keeping the string taut. You'll draw a perfect ellipse. Those two thumbtacks are the foci. For a planet's orbit, the sun isn't at the center like a circle. Instead, it sits at one of the foci. A planet's distance from the sun is not constant. Closest point, perihelion. Farthest point, aphelion. Think about Earth. Earth's orbit is nearly circular, but still an ellipse. In early January, we're at perihelion, 147 million kilometers. In early July, we're at aphelion, 152 million kilometers. That's a 5 million kilometer difference. Common misconception: changing distance causes seasons. Reality: the tilt of Earth's axis causes seasons. This law completely changed the game. Before Kepler, astronomers tried to explain everything with circles. They invented epicycles, circles on top of circles. Planets sometimes appeared to slow down, speed up, even move backward. It was a complicated mess. Kepler's first law swept that complexity away. A single graceful shape for planetary paths, a beautiful simplification. The universe could be understood through clear mathematical principles. Old, clunky models were replaced. The implications were huge. It's the rule of the road for everything orbiting the sun, the smallest asteroid, the largest gas giant. It's the shape of our cosmic neighborhood. Once Kepler figured out the shape of the orbits, he noticed something else about how the planets moved along those elliptical paths. This led to his second law, all about speed. You might think a planet just cruises at a steady pace, but that's not the case. The second law: a line joining a planet and the sun sweeps out equal areas in equal times. Show diagram. The takeaway: planets move faster when they are closer to the sun and slower when they are farther away. It's like a cosmic speed boost. Imagine a comet with a very elliptical orbit. Falling in from the outer solar system, it picks up speed. Near the sun, it whips around at perihelion. Traveling away, it slows down. At aphelion, it crawls before falling back in. That change in speed makes the equal areas rule work. Far away and slow, the line sweeps a long, skinny triangle. Think about Earth. In January, closest, Earth moves 30.3 kilometers, 109,000 kilometer reach. In July, farthest, 429.3 kilometers, 105,000 kilometer reach. This speed change follows conservation of angular momentum. Newton formalized it later. Kepler saw the pattern from raw data. It disproved uniform circular motion. Paths weren't circles, speeds weren't constant. Planets are in an ever-changing dance with the sun. The law gives the solar system a rhythm. It dictates changing seasons on planets and explains comets' fleeting appearances. It governs planets, moons, even artificial satellites orbiting Earth, a universal speed limit for when to speed up and when to slow down. Kepler wasn't done yet. After defining the shape of orbits and the rules for speed, he searched for a deeper connection, a master rule that would tie the whole solar system together. He wanted a relationship between how far a planet was from the sun and how long it took to complete an orbit. After another decade of relentless calculation, he found it. His third law: the square of a planet's orbital period is directly proportional to the cube of the semi-major axis of its orbit. In simpler terms, the farther a planet is from the sun, the much longer it takes to go around. Let's break that down. Earth is 1 AU and takes 1 year. Mars is about 1.5 AU, but its year isn't 1.5 years. According to Kepler's third law, we cube the distance 1.5 times 1.5 times 1.5 equals 3.375, and then take the square root. The result is about 1.88, and what do you know? A year on Mars is about 1.88 Earth years long. The math works perfectly. This law is like a cosmic calculator. It reveals a hidden harmony, not just farther are longer. A precise, predictable relationship governs all planets. It connects space and time. Know a planet's year, calculate its average distance. Know its distance, find how long its year is. This suggested the same physical laws governed the entire solar system, from Mercury all the way out to Saturn. The Tamsin now were sign the Tur Sansen Dayan in that wow. Where Simon's most distant known then, Kepler called it his harmonic law, a music of the spheres. Today we skip the musical metaphor, but the elegance is undeniable. It provides a powerful predictive tool. It applies to moons and to exoplanets orbiting distant stars, an ordered universe understood through mathematics. So, why do we still talk about 3 laws figured out over 400 years ago? Because they're the bedrock of orbital mechanics. We use them every day. When engineers plan a mission to Mars, they don't just point and go, they use Kepler's laws to design a Hohmann transfer orbit. A spacecraft follows a carefully planned ellipse, perihelion at Earth's orbit, aphelion at Mars's orbit. Timing is critical. Launch so the spacecraft and Mars reach the same point at the same time. It's all based on Kepler's rules. First law gives the ellipse. Second law sets speed changes. Third law predicts trip time, about 7 to 9 months. Voyager used these principles and planetary gravity assists to tour the outer solar system. Without Kepler, none of that would be possible. The same laws govern thousands of artificial satellites orbiting Earth right now. To place a satellite that hovers over one spot, use Kepler's third law to find the exact altitude. 35,786 kilometers for a 24-hour orbit. GPS satellites ride medium Earth orbits whose positions are constantly predicted using these laws. Every time you check the weather, make a satellite phone call, or watch satellite TV, you're using Kepler in action. Kepler's laws turned astronomy into a predictive science and paved the way for Newton's universal gravitation, explaining why Kepler's laws work. Even with supercomputers, Kepler remains the first step for orbital calculations. The universe runs on rules. Be observant, curious, persistent. Look up. It's not random lights, but elegant, predictable motion. And thanks to Kepler, we have the key to understanding it.